So today I'd like to tell you something about some recent as well as ongoing and future projects of mine that are all concerned with strongly correlated quantum impurity problems. Now, what is a quantum impurity? Quantum impurity is a particle, or more generally a discrete quantum system, that is coupled to a large ensemble, a bath of particles, or more generally a continuous quantum system. Now, this large ensemble is considered to be non-interacting or at most weakly interacting, so that all the relevant interactions happen between the impurity and the bath. Now, because I mainly work on strongly correlated systems, today I'm going to be discussing cases where the interaction between the impurity and the bath is strong. Now, if I had to choose one word to characterize impurity models, I would say that impurity models are simple. And I mean simple in two contexts here. Simple in the sense of easy, and perhaps with a more positive connotation, simple in the sense of fundamental. Now, as I hope to convince you in my talk, impurity models are not at all trivial, and in fact, it can be really challenging to obtain controlled quantitative results. But if you compare them to general quantum many-body systems, where each particle can interact with any other particle, then of course, quantum impurity models are much easier to treat because all interactions have to involve the impurity. And that's particularly crucial in numerics, where the scaling, the exponential scaling with the number of particles is unfavorable.
Screen for us, so we need to reshare.
Okay, sorry.
Sorry. Hi. So.
Can they still hear me?
I think they can.
Okay.
Oh, hello, Antoine. Well, no one complained yet. But, okay, so. Just go. Full screen. This is full screen, and then we share the.
Okay, so while you're working, let me just continue to say that despite, okay, thank you so much. Despite, of course, being much easier to treat than extended quantum many-body systems, we can already see many of the fascinating phenomena that we observe in generic quantum many-body systems in impurity models. And I listed just a few very famous examples that I'm sure all of you know. The Fröhlich polaron is an electron, or more generally a fermion, that interacts with the bath of phonons, so more generally bosons. And it is an impurity system that's really important to study when electron moves in a dielectric medium. Now, why this system is so important is that a lot of a very important numerical method, diagrammatic quantum Monte Carlo, that was pioneered by Boris and Nikolai, who was here until recently, was actually developed for the Fröhlich polaron. Another very famous impurity is the Kondo impurity, so spin that interacts with the bath of fermions. And the Kondo impurity, of course, is very important to study strongly correlated electrons in metallic systems. And the scattering on magnetic impurities is what's behind the Kondo effect that can also be observed in quantum dots. So here I found this nice picture of quantum dots that you can actually buy. They have a lot of really fascinating properties. They can emit light at very precise frequencies. And when it comes to spin and electron transport, quantum dots or other impurity systems I would say that it's probably fair to state that most calculations of transport are done on impurity systems such as these. And now finally, do I have to press another button? Ah, okay, thank you. Another motivation that I want to mention that we've heard about in many previous talks is dynamical mean field theory. Namely, if we do want to study an extended quantum many-body system for material science or condensed matter, we can utilize a mapping to an impurity in a bath And even though DMFT is an approximation because the lattice self-energy is considered to be momentum independent, and it is only exact in a certain limit, in fact, it works really well for several properties of strongly correlated particles. And in particular, you can observe the Mott insulator to metal transition. So it has had a huge success in studying strongly correlated systems. Now, of course, if you want to use DMFT, having a very good impurity solver is very crucial. Now, in my talk, I want to mention two different quantum impurity systems, the resonant Fermi polaron, as well as the Spin-Boson model. And I will also talk about non-equilibrium and dynamics for the Spin-Boson model. Now, what is a Fermi polaron? Perhaps you cannot see it. It's a mobile impurity that interacts with a sea of fermions. Now, due to Pauli's principle, the sea of fermions is non-interacting, and all interactions happen with the impurity. Now, what I consider here is attractive S-wave scattering. Of course, mobile impurities are very important to study electrons in metals, also helium mixtures. And if you come from a cold atoms context, then of course you can see the Fermi polaron as a limiting case of a strongly imbalanced Fermi mixture. So this is very relevant for experiments. And now, depending on the strength of the interactions between the impurity and the Fermi sea, you can have a different physical picture. So if the attraction between them is weak, well, then the impurity simply moves in the mean field of the medium, and you can treat this case analytically. As attraction grows stronger, then the impurity will excite particle hole pairs around the Fermi sea, and it will interact with these particles and the holes. If attraction is even stronger than that, eventually the impurity will form a molecular bound state with one of the atoms in the Fermi sea. And this Hamiltonian describes the system. We have here the kinetic energy of the blue impurity and the Fermi sea. And the interaction term here is a contact interaction where the impurity comes in and it can kick one of the atoms out of the Fermi sea, thus creating a particle hole pair. Now, this very simple diagrammatic element describes this interaction. We have the impurity come in with a certain momentum. It excites a particle and a hole. We have momentum conservation at the vertex, and the strength of this interaction is governed by the coupling parameter. Now, out of this very simple diagrammatic element, we can build a diagrammatic expansion, and we have heard about diagrammatic expansions in several previous talks, for example, in Nikolai's talk. So here, this is just an example for an expansion of the full propagator of the Green's function of the impurity. And this is just the full Baire expansion. This is not what we would actually sample diagrammatically, but it illustrates very nicely the physics that's happening here. So we have the blue impurity, and then it can create or annihilate a particle hole pair. And once a pair is created, it can interact again with a hole or a particle. And so you have all possible combinations of these interactions. So the diagrams can look very complicated, but remember that they're all built out of this very simple element that we saw on the previous slide. And so the goal of diagrammatic quantum Monte Carlo is to sample the series of diagrams without any truncation. So this means all possible orders, all possible ways to connect these vertices, and also all possible momenta and imaginary time values that are associated with these lines. Now, of course, we have many ways to do this more efficiently. We would not sample the Green's function, but the self-energy, so diagrams like this one would be forbidden. Nikolai was telling us about sampling determinants, so combining many of these into determinants, so you can use the bolt scheme, and so on. So there are many ways how you can do this more efficiently, but the takeaway message is that you need to sample the entire series without any uncontrolled truncations. And so this can be done numerically with Monte Carlo. So this is just a little cartoon that illustrates one of the possible ways of doing the Monte Carlo updates. So imagine we start with some low order diagram shown schematically here, and it corresponds to a low dimensional function inside of our integral. Now in the first step, we will sample this function at one particular value of its internal variables. And then we can do an update and sample, let's say, the same diagram or the same function at a different value of its internal variables. Then we can go ahead and we can stay at the same low order, but sample a different diagram at the same value of internal variables, or we can increase the order by adding a line here, which corresponds to a higher dimensional function inside our integral, and so on. And what's really nice is that we can utilize importance sampling. So in the end, we will end up sampling diagrams that contribute more to our expansion more frequently. So let's get back to the physics. I mentioned earlier that there is a polaron and a molecule phase in the system. So as interactions become stronger going from right to left here, at some point the molecule will become energetically favorable, the energetically favorable state. But as you can see in this plot here, actually both the polaron and the molecule are well-defined quasi-particles on either side of the transition. So this here is the interaction parameter, and this is the ground state energy of the system that was found by Nicola and Boris with diagrammatic Monte Carlo. So because you can see both polaron and molecule being stable on either side of the transition, of course, that tells you that the transition is first order. And this fact was actually discovered with the help of diagrammatic Monte Carlo. Now, what I did together with my collaborators was to look at the spectral function of the resonant Fermi polaron, which of course is also a very important quantity that can be measured in experiments and can tell us important properties of the system, such as the ground state energy, for example. So this is what we expected to see originally. Well, of course, we have a polaron quasi-particle, so we expected to see a very narrow, sharp peak at the ground state energy. And then we know that we can excite particle hole pairs with arbitrarily small energy. So we would expect the continuous part of the spectrum to start right after this polaron peak and have this shape. So we have no kinematically forbidden states here, and we expected to see such a picture also because the polaron remains stable on the molecule side of the transition. We expected to see the same there as well. But instead, we saw something like this, and you cannot see the top left corner, but so this happens close to the polaron molecule transition and on the molecule side. We saw this region here where the spectrum is anomalously low. It's not necessarily zero, even though it's consistent with zero within our error bus, but it is at least very strongly suppressed. And this happens even though we don't have any small interaction-related parameters. So K Fermi times A is approximately 1 here. And we called this this strongly suppressed spectrum the dark continuum. Now that's enough of cartoons. I want to show you some of our actual data here for the spectral function close to the transition and deeper in the molecule regime. And I will explain what these two lines mean in a second. Let me just first remind you how we get the spectral function. So first we compute the imaginary time Green's function with diagrammatic Monte Carlo. And then we have to extract the spectral function here from this integral equation. And Edwin in his last talk was just showing us something similar with a different kernel. And as he mentioned, of course, this is a mathematically ill-defined procedure because there can be many possible solutions for the spectrum A that are consistent with our Green's function G within its error bus. Now, most of these solutions will be extremely noisy. So one challenge is actually to find solutions that are physical. But as we discovered, that's only a small part of the problem. Because in fact, you can have several physical solutions that are very different. Or in other words, you can have two spectra that are qualitatively different from each other. So now I want you to look at these two lines here, but both of them correspond to Green's function, to Green's functions that are very, very similar within error bars that in our case are just a fraction of a percent. So it's just a mathematical fact that you cannot distinguish these solutions within even a very high resolution for the Green's function. So now what we did was developing a method that allows you to tell in a controlled or systematic way which features of the spectrum are actually there, are actually physical. So in our case, this is, for instance, the existence of this dark continuum, as well as the position of the polaron peak, and in fact also the position of this second peak, and which properties cannot be resolved with certainty, and in our case this is the width or the height of the secondary peak. So in other words, there's nothing you can do with the spectral function to remove these features and still be consistent with the Green's function data. Whereas the width here, you just cannot resolve. So the maximally smooth spectrum is actually quite broad, but our data is also consistent with a spectrum that is very narrow and sharply peaked. And in this particular case, we do know from ultra-cold atoms experiment that there is in fact a metastable quasi-particle on this side of the spectrum, which is called the repulsive Fermi polaron because it has a positive energy. So we do know from physics that the spectrum has to be narrow here. But in general, you have to be able in a controlled way to distinguish which features are real and which features you cannot decide on. And we provide such a framework, which is very general and can in fact be used with any method of analytic continuation that you choose. So be it maximum entropy or stochastic optimization with consistent constraints or anything else. So it's a very general framework that applies to all of these methods. So let me now switch gears a little bit. And I was talking so far about a mobile impurity system. Now I'd like to tell you something about a different impurity, which is a fixed impurity model, and also tell you a little bit how we can get to the dynamics of the system in a controlled and systematic way. So the Spin-Boson model is a spin or a two-state system which is coupled to an infinite bath of non-interacting harmonic modes, or in other words, bosons. And originally, this model was set up to study quantum dissipation because in a Hamiltonian formalism, energy is conserved. So if you do want to study dissipation, you need to couple your system to a large ensemble. And the simplest thing you can do is to couple it to harmonic modes. But you can also use it to describe interactions with photons or phonons. And as I will briefly mention at the end of my talk, this model can be used to study Fermi systems via mapping called bosonization. So this is the Hamiltonian of the system. It's comprised of the Hamiltonian of the two-state system here. You have your two levels. In fact, I will only be talking about unbiased systems where epsilon is 0. And then you have a tunneling constant delta between the two states. And this system is coupled to a bosonic bath, which is just a sum of harmonic oscillators. Now, the coupling between the two is a linear coupling here. And so CK describes the coupling of the system to a harmonic mode that has frequency omega k. Now, in the condensed phase, we can instead describe our harmonic bath by this spectral density function. And in the following, I will assume that this function is smooth below a certain cutoff frequency omega c, which defines the relaxation scale of the bath. And below this frequency, it scales like omega to the power of s. And then we have a certain cutoff function that can take different forms, like a Lorentzian or an exponential cutoff. What's interesting here is how differently the system behaves depending on the value of this exponent s. So the most studied case is the Ohmic case, s equals 1, which is the case that's most relevant physically. And in fact, a lot about it is known analytically. The super-ohmic case, where S is larger than 1, is trivial because in this case, the tunneling outweighs the weak coupling, and the system is always delocalized, which means that we're equally likely to find it in either of the two states. A very interesting regime is the sub-ohmic regime, where S is between 0 and 1, and it has a lot of really fascinating properties, such as the second-order quantum phase transition that I will get to shortly. Now, what we're interested in are dynamical properties of the system. This involves an evolution in real time, as we heard in several talks before, like in Martin's talk yesterday, on Guy's talk. You can do this on a Keldysh contour. So the problem here is, if you just look at a generic expectation value of a time-dependent operator, you can write it as an expression like this. And if we were in equilibrium, then these blue and red contributions would just cancel each other because we could commute every operator past the other. And what we would be left with is just the expansion of our initial density function, which we can do in imaginary time. Now, unfortunately, if we're out of equilibrium, or if we have a time-dependent Hamiltonian, or if we have a current flowing through the system, we cannot do this anymore because now the operators no longer commute. And so in our specific case, we start out with this in this state. So we start out in the 0-0 state of the system, so in one of the two states, and then the bath has just this thermal distribution. This is not our equilibrium distribution. So we have to instead evolve on the Keldysh contour. For example, we could start at a time t max, then evolve back according to this operator to time 0, and then evolve back to t max along the red part of the contour. And if we didn't know our initial state, then we could add an additional black branch here to the contour as well, but this is not what we're doing in this case. Now, we have to do this expansion in real time, which of course leaves us with a dynamical sign problem. I will get to how we can deal with it shortly, but first, let me just tell you about possible ways of expanding this Hamiltonian. We can expand in the diabatic coupling in this tunneling delta. That is one way. What I'll be talking about is an expansion in the system bath coupling, or in the interacting part of the Hamiltonian. And the nice thing about this expansion is that it factorizes our Green's function into the system and bath part. So the system part is a product of matrix propagators with the sigma z Pauli matrix. And the bath part, well, it's just your typical combinations that come from Wick's theorem, so you have to account for all possible ways of connecting these lines. So this is similar to the hybridization expansion, for example, for the Anderson impurity model. Now, how do we do this on the Keldysh contour? We can write our contour here, and then we have vertex insertions on either side of the contour, and our observable here will be at the fold. So what we do next is we just unwrap this contour, so we have it as one line, and then we can do our diagrammatic expansion in a very similar way as we do it in imaginary time, except we have to work in real time now, so we need to have an efficient quantum Monte Carlo method that can overcome the dynamical sign problem. And the method that we use here, this is work done in collaboration with Guy Cohen and Moshe Goldstein from Tel Aviv University. So we're using the Inchworm algorithm, which Guy really nicely explained in his talk. So the main idea behind the Inchworm, that calculating short time propagators is much cheaper than obtaining long time propagators, and you can recycle this information in each subsequent time step. So this reduces the scaling from exponential to polynomial. Now, I want to show you some results for the non-equilibrium population difference. This is the quantity we will mainly be looking at. So this is the expectation value of the sigma z operator, or in other words, the difference between the occupations in the two states of the system. So let me first show you some benchmarks from this paper by Theta Chen and Guy Cohen, collaborators. This is a benchmark for the population difference at weak coupling and in the high temperature regime, no bias. And you can see here that you can get to fairly long times. You get excellent agreement with other methods that work well in the high temperature regime. And we have two cases here for different cutoff frequencies of the bath. And another thing I'd like to mention is what you see here are coherent oscillations of the population difference, that it also kind of looks like, well, it will average out to 0 at the end of the time evolution. So this means the system is delocalized. It's equally likely to end up being in either state after a long time. Now, this is a more difficult regime, strong coupling, still high temperature. And this is just to show you how we have since improved our implementation, our algorithm. So it used to not be possible to obtain good results in convergence in this regime, but now we can obtain also quite long times in this more difficult strong coupling case. Now, what are interesting things to look at? So I've already mentioned that you can have the delocalized case where after a long time you're equally likely to be in either state, or you can have localization where the system is more likely to retain some memory of the state that it started out in, and then you can also have coherent oscillations versus just incoherent exponential decay, which is also sort of what you see here. Now, it turns out that there is, in fact, a quantum phase transition between the localized and the delocalized regime. So as you go to lower values of the exponent s and to stronger coupling, you enter the delocalized phase. You also have a changeover between coherent oscillations and incoherent decay. You can, in fact, have any possible combination of the two. And so what's really interesting is to study this quantum phase transition. In particular, what is not well understood really is the temperature dependence. So what happens when we crank up the temperature? So these are, by the way, 0 temperature results from these two groups. What actually happens when we turn on the temperature? Will we get some interesting behavior in the quantum critical fan? What do the exponents look like, and so on. And the numerical challenge here is that there are methods that work really well at 0 temperature. There are methods that work really well at high temperature, while our method works very well across all temperatures. So we're really in an ideal position to answer that question. And I want to show you some very preliminary results as of yesterday for something that you can see. So you probably cannot see all the labels, but what I'm doing here is I'm going from a larger to a smaller value of the exponent s. This is all fairly strong coupling and a large cutoff frequency. And the different lines are as we increase the temperature from a very low temperature, so beta equals 50 and 10 and even 5, you can barely distinguish these lines here. So this is pretty much the 0 temperature regime, and you can see how as we increase the temperature, something changes. So we tend to go from coherent oscillations to incoherent decay, but then also as we decrease the value s, you can see how the system here is actually delocalized as opposed to this limit, but as we turn on the temperature, it actually becomes localized and incoherent. So this is just a preliminary outlook on what we can do. And so what we plan to study is how the system behaves as we change all of these parameters. Now, just to give you a little outlook on what else can be done, it would be extremely interesting to look at the heat current through the two-level system if we couple it to two harmonic baths at different temperatures. So will it look the same as if we had just one bath in the average temperature, or will we be able to observe some more interesting physics? And then, of course, our method is really general, so we can, in fact, combine bosonic and fermionic bath, which is important if you're interested in studying superconductivity. And finally, as I mentioned at the beginning, there is a mapping called bosonization between an electronic system and the Spin-Boson model. In fact, so this is one site which is coupled to one or two or several interacting electron leads. And now, of course, interacting 1D electron leads are really important because in 1D, the assumption of non-interacting leads is not justified. So this will give us a great opportunity to study this regime. So I think I'm out of time. And let me just conclude. I hope that I could present you two very interesting quantum impurity systems and convince you that these are very important and that they can be studied with controlled precision, with controlled numerical methods. Thank you very much, and I'll take questions.